Hi everyone, my name is Lilow. I'm a postdoc at the Technion in Israel, where I work together with Adi Nasser. And today I would like to talk about this recent paper of ours, where we generate constraint realizations from the 2 mass Redshift Survey to probe structure growth. Now, most of the time when you think about probing structure growth, you probably think about using large-scale statistical properties of the meta distribution, like the meta power spectrum or the halo mass function. However, today I want to talk about one of the ways you can instead use the specific 3D distribution and flow of matter in the local universe to do so. For this, we use that on sufficiently large scales. This linearized version of the continuity equation holds, where the divergence of the peculiar velocity field is directly proportional to the matter over density. And proportionality constant is given by the growth rate f, which in turn is related to the matter density parameter. There's also the Hubble function h appearing here. This, however, is absorbed into our distances, and everything is expressed in terms of megaparsec over h. Now, of course, we do not directly observe the meta distribution, but instead galaxies tracing that distribution. So we have to account for the galaxy bias here, which we do approximately by the ratio of the meta sigma 8 and the galaxy sigma 8. And then the second step, we define this normalized overdensity as this ratio here, which can be directly inferred from the observed distribution of galaxies. And then this suggests to constrain this cosmological parameter combination f sigma 8 in 2 steps. First, we use a Redshift survey from which we reconstruct this density contrast, and then use this relation to obtain the peculiar velocities, which still depends on this parameter combination f sigma 8. Then the second step, we compare this reconstruction to some independently observed peculiar velocities to constrain f sigma 8. So let me start with the reconstruction part first. For this, we use 2MS, the 2 mass Redshift survey, as an input. Contains approximately 45,000 galaxies. It's an all-sky survey in the sense it covers everything except for the thin slice obscured by disk and bulge. It has an effective depth of 0.05. So it is rather shallow, but it's the densest all-sky Redshift survey we have to date. Within this well-defined flux limit, it has full completeness and is sufficient for our purposes to obtain a reconstruction out to a distance of 200 megaparsec of h. Now, for the reconstruction itself, we combine and extend different pre-existing methods. First of all, we follow Fisher et al. 95. The first step is to correct for redshift space distortions, as the redshift position of galaxies that we observe have to be related to the real space positions, which is given by this correction in the peculiar velocity along the line of sight. So in line with our linear theory assumption, we relate the real space and redshift space over densities by linearly Taylor expanding to first order in peculiar velocity, allowing us to correct for these distortions in a self-consistent single step, rather than having to do some iterative process. And afterwards, even when we're in real space, we still have to take into account that we have observational noise. So since we observe a discrete set of galaxy traces, there's short noise, and we address this by applying a Wiener filter. So the Wiener filter is given by the cross covariance between sigma and data divided by the data-data covariance. That means in those regions of the data where signal noise is high, the data is approximately given by the signal. The Wiener filter approaches 1 and leaves the data pretty much untouched. However, in very noisy data, this inverse covariance suppresses the data, meaning it's a conservative filter that focuses on the high signal noise regions. It also has the property of being an optimal linear filter in the sense that it minimizes the variance between the reconstructed signal and the true underlying one. There's still different choices of the space in which we apply this filter. We could do it just in normal, directly in real space, but this is very expensive because we have to invert a matrix for like a 3D grid of points. So usually you would go to Fourier space to diagonalize the problem. However, there are 2 effects which prevent us from doing this. First of all, our shot noise is not constant everywhere, but since we have a flux limit survey, and you see the redshift distribution of 2ms here, it decays with distance, and therefore the shot noise increases. So we have a radial dependence of shot noise. And together with the redshift space distortion along the line of sight, this leads to a coupling of radial modes. So Fourier space wouldn't be diagonal. However, so-called spherical Fourier Bessel space is a better option. So there you expand all relevant functions in terms of spherical harmonics and spherical Bessel functions, and has the nice advantage of all these angular modes L and M being completely independent from each other, and there's only coupling between the radial modes. So in that sense, this is the maximally diagonal space to perform these operations for all square surveys, meaning it's more efficient and also much more scalable than real space reconstructions, since this doesn't scale with volume, but with the depth of the survey. So what I show down here is now this result of the Wiener filter applied to the 2ms data as a slice through the supergalactic plane of colors and contours showing the density contrast and the errors to the peculiar velocity field. Can nicely identify some of the known dominant structures, like Virgo is right here in the center, Coma is up here, and further out we have the Shapley supercluster. Now there are 2 points we still need to address. One is the Wiener filter does not only suppress noise in regions where it's very noisy, but also the signal there. So we have to reinstate this power. And secondly, we would like to have some way to faithfully estimate the errors of a reconstruction. And both of this is addressed by the method of constraint realizations, which generate the whole ensemble of realizations that are all compatible with the noise observations, rather than just looking at one estimate. And there we adapt the efficient method of Hoffman Ribak from 1991, which essentially has 2 steps. First, we have to generate a random realization of the underlying signal, so for which we assume that we have some correlated log normal distribution for density contrast. And then, given such a random signal realization, we generate the respective data realization by performing a Poisson sampling. Once we have these 2 ingredients, we apply the Wiener filter to this random data generation, subtract this from the true random signal, and this together is then a residual correlated noise contribution, which we add to the Wiener filter estimate of our real data. So this together gives us then, if we repeat this process for a number of randomizations, gives us a whole ensemble of constraint realizations. Now, this whole procedure is exactly is the exact constraint realization in the sense of precisely sampling from the full conditional probability distribution only if all of the signal and data distribution functions are Gaussian. However, even if they are not, as is the case for us, this way of defining constraint realization still is accurate on the 2 point, on the variance level. So meaning that the scatter between these constraint realization and the Wiener filter estimate correctly describes the scatter around the true underlying fields on the variance level, which is perfectly sufficient for our purposes. Down here in the lower right, I show one of these residual signal noise realizations, where you can visually already see has a very small amplitude in the center, where our data is not very noisy, and the amplitude increases towards the boundaries. And we quantify this also by looking at the scatter between different constraint realizations, which is shown here as a function of radius in blue for the density contrast, orange for the pure velocities. And this quantifies our statistical reconstruction uncertainty. So near the center, very small for the velocity below 100 kilometers per second, but then increases towards the more noisy boundary, outer regions of our reconstruction, where it slowly approaches the intrinsic cosmic variance of these fields, which is marked with a dotted line, as expected. Now, given this reconstruction, we have to compare it with observed velocities, for which we use the Cosmic Flows 3 catalog. So Cosmic Flows 3, or CF3, is a compilation of different galaxy distances obtained with a variety of heuristic methods, most notably Tyler-Fisher and fundamental plane relations, but for example also type 1a supernova. Contains around 18,000 galaxies distributed over a bit more than 11,000 groups. And you can see a plot of its distribution here on the right, where different colors correspond to different subsets of CF3. You can directly see, unlike 2ms, this is not isotropically distributed on the sky, but that's not a problem for us because at this stage, we only do point-by-point comparisons and don't require isotopic. So how do we compare them? We look at the distance moduli because these are the quantities directly constrained, observed by cosmic flows. So we look at the difference between the observed distance moduli and the one we expect given the observed redshifts, corrected for our reconstructed peculiar velocity. There are two more things we have to take into account. First of all, our velocities inside 2ms also have notable contributions from the sources beyond our reconstruction volume. So we describe those by allowing to fit an additional global bulk flow contribution, the external. And secondly, this translation from redshifts to distance moduli depends on the value of H0, which in our analysis is treated as a nuisance parameter because, for example, it will also absorb any potential systematic errors in the 0-point calibrations of CF3 distance moduli. So then we perform a chi-square minimization where we fix these parameters for each individual constraint realization of the peculiar velocity fields going in here, find the optimal values for each of these realizations, and afterwards take the average over a large set of constraint realizations. So the error then has two contributions, one from the average chi-square fit error, which accounts for CF3 distance uncertainties, and the other from the scatter between the values obtained for different velocity realizations, which accounts for the shock noise in 2ms. So if we do that, the result for f∑8 that we get is shown here as a function of the smoothing scale we apply to our reconstruction. As you can see, this has a very significant dependence, which is caused by the fact that we compare a smooth linear peculiar velocity prediction with unsmoothed directly observed peculiar velocity. And it had been shown before that this leads to a smoothing scale dependent bias, which is caused by the difference between true and reconstructed velocities being correlated with the velocity estimate itself. There are different methods to avoid or correct for this bias. The way that we choose to do it is to use mock galaxy catalogs. So for this, we take the multi-dark simulation one, MDPL2, which comes with a nice semi-analytic galaxy catalog from which we generate mock 2ms and CF3 catalogs, imposing the actual survey characteristics on those. Now we have to be careful not to just take any random subvolume of the simulation, because any deviation from the specific flows that we find in the real universe could lead to systematic errors. So we apply a set of criteria to find regions which are very closely representative of the local group environment. So for example, there has to be a local group type halo of the correct mass, same for Virgo in the proximity to right distance, and also the absolute and relative velocities of the local group and Virgo have to closely match the observed ones. So for this, we find 17 mocks that we use for our tests and calibration, where I show one example down here, the true simulated fields on the left, our reconstruction on the right, and you can directly visually see there's really good agreement between both of them. Of course, becomes more noisy towards the boundary as expected, and there is some suppression of very high overdensities, which is fine though for our case, since we're mostly interested in the peculiar velocities. So what we do then is we apply exactly the same analysis pipeline to the mocks as we did for the real data, compute the average over f∑8 for all of these mocks, and then take the ratio between the true simulation value and this average estimate and multiply this to the our raw estimate of the real data. And the result is shown as a black line here. And compared to the original raw estimate, you can nicely see how it completely got rid of this spurious redshift scale dependence, giving us a robust estimate of the true value of f∑8. There's one additional advantage of doing this calibration using realistic mock catalogs, because now these error bars here also, to some approximation, contain the systematic errors introduced by approximations in our reconstruction method. For example, that down here at very small scale, the linear theory assumption wouldn't work anymore. To be on the very safe side and don't rely too much on the correctness of these error estimates on very nonlinear states, we use the slightly more conservative result found at the smoothing scale of 15 megaparsec over H as our final result. And we take this value, and to compare it with literature, it's conventional to multiply it with the ratio of the linear and nonlinear sigma 8 to really end up with this cosmic parameter combination F times sigma 8 linear, which we compare with other values in literature down here. So all the points are different local measurements at different redshifts of F sigma 8 linear, where our result is the black circled one here. Colors represent different methods of doing this. So all the orange points correspond to some variation of comparing a linear velocity prediction with a set of observed velocities. And the gray bands show the 1 and 2 sigma intervals of Planck, so obtained from CMB. So a couple of things I want to mention. First of all, our results are perfectly consistent with all the other local measurements. And also at the 1.1 sigma level, they agree with the Planck results. So we cannot see any systematic deviation from lambda CDM from our analysis. And lastly, I want to mention that our error bars are quite a bit larger than some of these which use a similar method than us. And this really boils down to us also taking into account all the systematic errors by doing a proper calibration on realistic mock catalogs than rather only relying on the much smaller statistical errors. So in a sense, our results are more representative of the true uncertainty in this value with this method. And lastly, I want to talk about bulk flows. So first of all, our external bulk flow contribution that we found was of the order of 200 kilometers per second, which is rather sizable. For example, accounts for approximately 20% of the motion of the local group, which is in line with what had been previously found. And down here, showing the total bulk flow, so the sum of the 2MS internal reconstruction with this external bulk flow component. Our result is the black line with 1 sigma contours in gray. And as you can see in the comparison with a variety of different local measurements of the bulk flow, we have really, really good agreement. There's only a bit larger deviation to this point, which is an overall outlier. Lastly, you can also look at a radius of 0. So basically, this is our reconstruction of the local group motion. And this also excellently agrees with the observed CMB dipole, both in amplitude as well as direction. With this, I would like to come to an end. I hope I could show you that Wiener filter-based constraint realizations of a redshift survey such as 2MS provide robust estimations of the fields, including faithful estimation of statistical errors, that it is really crucial to use realistic mocks to both calibrate our results and to account for systematic errors, which can be quite large. Then by combining our reconstruction with the velocities from Cosmic Flow 3, we got consistent competitive constraint in the growth rate as well as the bulk flow. And lastly, I want to mention that the code we wrote for this called CORAS is publicly available on GitHub, free for anyone to use. Given our method is really efficient, it takes about a minute to generate a constraint realization on a laptop. Let me just finish with a short outlook. Would like to extend this also to photometric redshift surveys, so we have to account for the redshift errors in those. We'd also like to directly include the observed peculiar velocities into our Wiener filter approach, rather than having to compare with those in a second step. And in the long term, want to prepare all of this to be applied to the next big all-scale survey, CEREX, which will reach much higher redshifts above 1 and increase the number of galaxies by a factor of 10,000. So there, the efficiency and especially the scalability of our approach really will become important. And with this, I am at the end. Thank you for attention. I'm looking forward to the discussions.